All right, we're going to use Euler's method to get a numerical solution, an approximation for the differential equation x prime equals t minus x. Here, x is seen as a function of t. So this is really x prime of t that we're given, and what we want to find is the function x of t. Now, when we solve it numerically, when we get a numeric approximation, what we're going to be doing is not finding the equation, but really finding a series of points on the interval that we're interested in here from 0 to 2. And at the end, we could sort of plot these points and see like a sketch of like kind of roughly what this curve would look like by plotting those points. At the end, we'll also find the solution analytically. So we'll get that function, the exact solution, and then we could sort of compare their graphs on that interval. So here they've told us that the initial condition is x of 0 equals 1, which means when t is equal to 0, x is equal to 1. And that's our initial step, step 0. When t is equal to 0, x is equal to 1. That's sort of our seed for this algorithm. And in order to find our next value of x, what we need to do is figure out what our delta t is. And, you know, that's fairly simple. We're looking at the interval from 0 to 2 using n equals 8 steps. So this was just like you might remember way back in Calc 1 when we were learning how to approximate the area under a curve. We had to find our delta x, you know, like how wide each of those rectangles are. This is the same thing. This is the same calculation. So our delta t is simply 2 minus 0. So I take these endpoints here, right? Take the right endpoint minus the left endpoint, and then I divide it by the number of steps. So 2/8 or a quarter, 0.25. Now, as we go through this, we're going to get numbers with decimals that go and go and go. We're going to try to maintain as much accuracy. So I'm not going to truncate these numbers much. I'm going to write them all the digits out that my calculator gives me. Most of the error that is introduced when we use Euler's method actually comes from that truncation. So I'm going to try to use all the digits my calculator will give me. When more powerful computers are used, you get even less error because, of course, when you program in the algorithm, the computer has the ability to kind of carry many, many more digits. And so I set up the table like this. So here's our initial step at t equals 0 and x equals 1. Our x prime, well, that's just our equation, t minus x. And so I'm just taking the subtraction. I'm going to take 0 minus 1. I'm literally just doing this operation using these columns. So I get negative 1 for x prime. And then my next value of x is I'm going to take the current value of x, which is 1, and I'm going to add x prime times delta t. So x prime is negative 1 times delta t is 0.25. Delta t doesn't change. That's constant always. And that will give me my new value of x. So in the calculator, well, actually, I guess we don't really need a calculator for this one. 1 minus a quarter is 3/4, so we have 0.75. Now these values of t in this first, you know, blank column here, these are I'm just gonna step up by 0.25 each time. So I've got 0, 0.25, and actually we can fill out this column entirely right now. 0.5, 0.75, 1, 1.25, 1.5, 1.75, and 2. Okay. Now all the other ones we kind of have to keep doing these calculations to kind of fill out the rest of, you know, this column. And then together, the set of points from these two columns will give us coordinates that we can plot. So now I'm going to keep going. T minus x is 0.25 minus 0.75, and that gives us negative 0.5. And then for our next value of x, I take the current x, 0.75, plus x prime times t. I get 0.625. That goes here. Then I keep going, right? T minus x. So 0.5 minus 0.625, that'll give us a minus 0.125. And then we use this again, so we take current x, 0.625, plus x prime, negative 0.125, times delta t, .59375. And I keep going. 0.75 minus 0.59375. So here I'm going to use just a really handy feature. If I do second and then the negative sign, I can bring up a and s. Let's just use the previous answer. So I'm going to do 0.75 minus that value, and I get 0.15625. And now I'm going to take the old x, 0.59375, plus 0.15625 times 0.25. Oops. So 0.59375 plus, here's my x prime, 0.15625 times 0.25. 0.6328125. And then again, right, it gets pretty repetitive. T minus x, 0.3671875. And then again, let's see, 0.6328125 plus, and then our x prime of 0.3671875 times 0.25, 0.724609375. And then again, t minus x, 1.25 minus the previous answer, 0.525390625. And then the old x, x prime times delta t. Point 855957013. And again, .64404, 29688, old x, plus x prime times delta t. 1.016967773. One more step. Last calculation. Old x plus delta t, or sorry, x prime times delta t, which is 0.25. 1.200225583. And once we find the value of x that goes along with our last step, when they told us to use n equals 8 steps, that's when we stop. Okay, so now this set of values, these two columns here, we could think of them as a set of coordinates. What I'm going to do is plot them. I'll throw them in the calculator. Of course, I'm going to have to think of the x, the t values as x and the x values as y, because the calculator likes x and y and not t and x. But you know, the t's are our input values, the x's are these outputs. So what I'm going to do to put them in my calculator to kind of see what I've found is, so I've actually already entered these values into my lists, but here's how you do it. You hit the stat button that's right next to the arrow keys. So I'm going to hit stat. The very first option is edit. I'll hit edit, or I'll hit enter on that option. So you can see my there are my t values in the first column and my x values in the second column. Now it looks like these x values have been truncated, but that's just because the column width is fixed in the display. But as you scroll down, it does display the full value here. So I've put those in their entirety, or at least all the digits I have from the calculator into that column. So the way I can get see a plot for these values, I'm going to hit the stat plot. So I have to hit second, and then the y equals will be stat plot. Right now everything just says plots off, plots off, plots off. So on the first one, I'm going to tell it that I want to plot some data. I'm going to hit enter on the first option. I'm going to hit enter here to turn that plot on. That first entry, that first list here under type, I'm just going to have it do a dot plot. I'm telling it to make the x coordinates correspond to the L1, or those t values, and the y coordinates, those outputs, correspond to L2, or those x values. And at the bottom I could tell it what marker to use, and I'm going to have it use those hollow squares there. Now if I hit graph, we can see these are the squares, and we kind of get a picture of what this curve looks like. If I go back to the stat plot options, and instead of just telling it to use dots under type, the second one is like a broken line graph, or like it just sort of connects those dots. So I can have the calculator kind of sketch it out by connecting them, and it looks kind of like that. So we get an idea of what this function looks like on this interval. Now let's solve this. Let's solve this analytically, and maybe we can compare what the actual graph of the exact solution is to what our dot plot looks like. So our x prime, I'm going to call it dx dt, is t minus x. And to solve this, I'm going to use a substitution. I'm going to let u equal t minus x. And that means that du dt is equal to 1 minus dx dt. And that means that dx dt is 1 minus du dt. So making the substitution, I have 1 minus du dt is equal to u. I'll solve this for du dt, a little algebra here. Du dt is equal to 1 minus u. And rearranging, separating the variables, remember doing that from a while back. I'll divide by 1 minus u both sides and multiply both sides by dt. So we get du over 1 minus u equals dt. Now let's integrate both sides. We have on the left side, that's a ln rule, so this is minus ln of 1 minus u is equal to t plus some constant, I'll call it c1. I'm going to zap both sides with a negative, so ln of absolute 1 minus u is negative t plus some other constant, c2, which is the same as negative c1, but I'd rather not carry through many negatives, so I'm just going to call that a new constant. Rewriting this log in its exponential form, we get absolute 1 minus u is e to the negative t plus c2, and using rules of exponents, that's the same as e to the c2 times e to the negative t. Now this is absolute 1 minus u. It makes sense that this would have to be positive because of e to the c2, right? E raised to any power is going to be positive. But that's the absolute value of 1 minus u. That means that 1 minus u itself could be negative, and the way that that'll be reflected here in the solution is this e to the c2, I'm just going to call it a new constant. I'll call it c3. E to the c2 is some constant. Now we know that's positive. c3 could be positive or negative though, right? I've dropped those absolute value signs. Multiplied by e to the negative t. Got a little ways to go because of course we want a solution for x and not 1 minus u. So I'm going to just rearrange this to solve for u first. So negative u is c3 e to the negative t minus 1. I'll zap both sides with a negative so that u is, and that's a negative c3 e to the negative t, and as you might predict, I'm just going to call that a new constant, c4. So I have to chase negatives around a little bit less, and then plus 1. Now I can substitute u, make my substitute back in. U is t minus x. And I can solve for x now. So negative x is c4 e to the negative t plus 1 minus t. And this, I'm going to zap both sides with a negative, and again, I'm just going to, instead of chasing through another negative, I'm just going to call this c5, like a new constant. So here's x is equal to c. In fact, I think it's my last constant, I'll just call it c. c e to the negative t plus t minus 1. Now, we have this unknown constant, but they gave us an initial condition, so I'm going to use that initial condition to solve for c. So they told us that x of 0 equals 1, and that means that 1 is equal to c e to the negative 1. Oh no, sorry. T is 0, so e to the 0. And then plus 0 minus 1. And that means that, let's see, e to the 0 is 1, so we have c minus 1. This means that c is equal to 2. And so that gives us our exact solution, x of t equals 2e to the negative t plus t minus 1. So there's exact. So I did this so that we could kind of compare the exact result to what we plotted. So I'm going to put this function here into the y equals editor. And of course I have to use x's instead of t's, but that's fine. 2e to the negative x plus x minus 1. And let's graph it. In fact, I'm going to change the color. Make that one red. So, pretty close. We could see that we start introducing error, we could get an even better approximation if our delta t was smaller, if we used more steps. Just like we would get a better approximation when we were approximating the area under a curve back in Calc 1. All right, we're going to do another example of Euler's method. This time our equation is x prime equals 0.2 times tx. I'm just going to fill that information in here in this column. That's how we're going to fill out that column of the table. The interval is from 1 to 1.5 with 10 steps. So for our delta t, 1.5 minus 1 over 10, that gives us 0.05. We can use that to fill in that first column. Now our initial condition, x of 1 equals 1, so when t is 1, x is 1, and we fill that in for step 0, those are the initial values. And I could fill in the t column using our delta t value. Okay, well, let's get going. We're going to fill in this first x prime value, 0.2 times tx. So 0.2 times 1 is, of course, 0.2. And then our new value is old x, so it's 1 plus x prime times delta t, 0.2 times 0.05. And that gives us 1.01. And then again, 0.2 times tx, so 0.2 times 1.05 times 1.01 is 0.2121. And our new x, we're going to take our old x, 1.01, plus x prime, 0.2121 times delta t, 0.05. Delta t, so second answer, times 0.05. 1.02605. And then again, right, over and over again, 0.2 tx. So .2245331. Of x plus x prime times delta t. .031 83165. And again, 2 times two, 3, 7, 3, 2, 1, 2, 807, and then old x plus x prime times delta t. 0.05. Old x plus x prime times delta t. 1.043697719. 2tx. So this is all, of course, very repetitive. Two tx. Oh, 229. And then again, old x. One point 069424868. Okay, 1.11. Finally, the last calculation, old x plus x prime times delta t (1.129466,836). Okay, and this is where we stop. We've got the final x value that corresponds to our last t value. We could, like in the last example, plot these points and kind of get a sketch, and we could sort of see, as we did in the last example, like how close or far away it seemed. We can actually calculate how close or far away it is too. I mean, the further away you get, I mean, our exact known value is just the initial condition, is just what's going on up here at 1, 1, right? So that's the only one we know for sure. The further away you get from that, the more error you introduce, because we're essentially just using little bits of tangent lines, right, at each of these values of t to predict the next x. And then we're using that predicted x, which has some error, and then using a tangent line at that point. So the further away you go from your initial position, the more error there is. So if we want to get a sense for like how off we are or how close we might be, we can compute a % of error just at this last value, right? So to know overall like how far astray we've gone, we can compute the % error at this last point, as long as we can figure out what the exact solution is by analytic means. And we can do that in this example. So our equations of x prime, again, I'm going to use dx dt. We have 0.2 tx. I can multiply both sides by dt over x to separate the variables. And then we have dx over x equals 0.2 t dt. And we can integrate both sides, right? No substitution needed. We're able to separate the variables as is. And so on the left side we have ln of absolute x. On the other side we have, using the power rule, 0.1 t squared plus a constant. Call that c1. Again, we could rewrite this equation in its exponential form. So absolute x is e raised to this power. We use the rules of exponents. So we have e to the c1 times e to the 0.1 t squared. That's absolute x. Now just with the last one, of course, absolute x has to be positive. That's reflected because, of course, e raised to any power is positive. But x itself could be negative. And so I'm going to drop these absolute value signs, and when I do so, I'm going to change this to a new constant. I'm just going to call it c, because c could be positive or negative. So we have our general solution. Now we'll use our initial condition. So if x of 1 equals 1, that means 1 is equal to c times e to the first, or sorry, 0.1 times 1. So that's e to the 0.1. c times e to the 0.1. That means that c is 1 over e to the 0.1, which I'm going to rewrite as a negative exponent. C is equal to e to the negative 0.1. Okay, Now we have that value c. That means that we have our exact solution. X of t is e to the negative 0.1 times e to the 0.1 t squared. I'm going to use rules of exponents to clean this up a little bit. E to the 0.1 t squared minus 0.1, and I'll factor out that 0.1 in the exponent just for convenience. So there's my exact solution by analytic means, right? the particular solution rather by analytic means. And to calculate the percent of error, the first thing I'm going to do is just figure out, well, what is this function here tell me we should get when we plug in 1.5, right? That's the end of our interval. I get 1.13314,853. Okay, so now to find the relative error, I'm going to take the actual value, what we just computed by using the function that we found here, the 1.13314,853, minus the predicted value, what we got when we used Euler's method. I'm going to divide by the actual, right? I want to find the difference compared to what the actual value is. So that's what I'm going to divide by the actual, and then I'll multiply by 100. So we get the following calculation. Our predicted value divided by actual and we get about times 100, 0.3249% approximately. So less than 1% error at the end of that interval. Pretty close. We could make our predicted values even closer if we used a smaller delta t, took more steps.